Hello everyone. Today I'm going to talk about how we built Orange Trail, and especially focusing on how we built a composability around the contracts because we have several contracts for Orange Trail. And so I'm going to talk about how we made this on the back end, on the front end a little bit, and on the contract side most of all, so that you can get some inspiration and a better understanding on how to build this kind of complex application. So I've opened the repo. It's called DGen Poddy because that used to be the name of Orange Trail before we renamed it. I'm going to walk you through this repository quickly. So the way it's structured is you have the front end code in the front folder, you have the backend code in the DGen Poddy folder, and you have the contracts in the contracts folder. Everything else is either not very important or just stuff from my dev copy, kind of dirty. So Orange Trail, the idea of the game is that it's kind of like a board game, party game hybrid. You have a board, you move on that board, and then every turn, every day, some random event happens. And based on what the random event does, things are happening, and then you move on. And the idea is that you bet some orange token and you get oxygen token out of it. So the front end is basically like a Vue and Vue app. It's relatively straightforward. We're using WebSockets to interact with the backend. So we have like a WebSocket class to just handle that. We have the data structures from the game copied in TypeScript and like interaction there. And then we have the components for the various phases. The component for the board, the component for the crash game, header, the lobby, everything. It's relatively straightforward code on the front end. One interesting aspect is the animation system that I've implemented that makes it convenient to time things, relatively speaking. Because like this is kind of an optimistic behavior. Sometimes the front end does things optimistically and then it needs to wait for the back end to react and make sure things happen. So we have a synchronization system that mostly works. It's not the most reliable system, but it's working for our purposes for now. The more interesting things are on the backend side and on the contract side. So like I said, we have several contracts for Orange Trail. Right now we actually have two. So we have the main contract, which we've called board game. Names have not been the best thing about this project. The board game is essentially handling the state of the board, and so it's what happens on like the like high level. We got a contract, and then we have potentially one contract per type of mini game, and we've only implemented one mini game, which is a crash game. So we have the contract for the crash game, and so each contract lives in its own folder. It's its own crate inside the contracts folder. The contracts folder is an SP1 essentially it's an SP1 project. So built with Substance Lab SP1. You have a build script that just recreates both the metadata file that like basically generates the guest programs for the RISC-V ZKVM, and it stores it inside the /elf folder. And so that's how you include it, and then you have each of the programs. If you look at the code inside the server, when we run the program, we have our main function here, and one of the things it does is call a module. So this is, as usual for the Hyli applications, using some of the same systems as our full node. We have like a whole very modular system with modules that interact through a message bus. And so like this is the setup code for this. And then one of the module ensures that the contracts are registered. So it just like registers the contract if they don't exist on chain by calling an API to check the state of the contract. If they don't exist, it registers them. Then we have a module for the WebSocket that's provided by Hyli. Like this is part of our SDK. You have the structs that define the messages that go in. The messages that go in, for example, say submit an action or send me the state. Maps the messages that go out or mostly just updates to the state of the applications. And then we have the rollup logic of Orange Trail, and we have the prover logic. So for the prover logic, we have other in-depth videos that will go more in-depth about this, but what I'm going to talk about quickly here is how we've managed to implement the rollup logic for Orange Trail. So like the idea of Orange Trail is that we wanted the game to be kind of real time, especially like the crash game needs to be kind of real time. So the crash game, like the rocket starts, multiplier up, goes up, goes up, goes up. You can cash out at any time, but you want to cash out before it crashes to zero, because at this point you've lost your money. And to do this in real time, we need to have a rollup. So essentially what we have is a basic rollup. All the transactions go through a single centralized sequencer that manages its own lane of transactions. And so in the contract, we have code to ensure that. Then we need to make sure that we manage interactions with other contracts correctly. So the important part here is that we need to be aware of a lot of things to make things work properly. And actually the rollup execution module is kind of complex. The setup function essentially creates the initial application structs, the application data, and then it builds the module and it registers all of the contracts that we're going to want to handle and all of the functions that are going to handle the logic of each of the contract we're interested in. So we're interested in the board game contract, we're interested in the crash game contract, obviously. We're also interested in token contracts because we want to make sure that users have enough tokens to actually, bet at the start of the game. So we're interested in the oxygen and the orange token contracts. We're interested in the wallet contracts because we need to know that the user wallet exists, and we're interested in this built-in verifier for SecP 256K1 curve. So these are all of the contracts we're looking at, and so we need to be able to run all of the logic here. And so some of these things, like the light wallet executor, the light sparse Merkle tree token executor, are defined in other crates. The logic for the board game and the crash game are defined inside of Hyli itself. And so essentially, like what happens then is that every block we process the transactions that we care about optimistically. So we have a function handle optimistic transaction that essentially just processes each transaction. We have some logic here that checks if this is a transaction that's interesting for us based on like the contract names. And if it is interesting for us, then we execute all of the blobs. We reflect the state changes locally to the optimistic state. And then we send WebSocket updates for like the new state of the game after each transaction. And the thing is that this happens, there's several steps that can happen. And so the first thing is that we receive the transaction through like the rollup mode. We execute it locally. But sometimes we need to make sure that we're synced with the chain and stuff. So we receive it again after the consensus happens when we receive the new blocks. And then we reprocess those optimistic transactions with information from the consensus. And so we have a logic of data quality where the first level of data quality is the rollup system, which is like internal. And then we have the consensus level of quality where at this point, like, things have happened, we know which order things are in, so we can like for sure execute this. And so the logic of the rollup executor is essentially to maintain two different contract states. One of them is the optimistic state, and one of them is the settled state. And so the settled state we know for sure is good. And sometimes we need to rerun, for example, if a transaction fails unexpectedly, we need to rerun all of the transactions from the settled state. And so this rerun from settle does that in an asynchronous manner to be more efficient, but essentially like the idea is you rerun all of the transactions optimistically on top of the settled state, and you arrive to the correct state you'd expect. And so what this allows us to do is we can predict if you don't actually have a token, so you can't actually join the game. We can correctly skip incorrect transactions, and we can also still, in real time, show you what happened within the game. The architecture of this rollup execution module, this is probably gonna, this is not the final form that this should take. This was kind of our first try, and there's a few things we'd probably do differently to do it right now. The whole idea of keeping settled state and an unsettled state is kind of nice, but we kind of wanted to have better performance. We ended up cloning a lot of data. This wasn't necessarily super fast. I'm not handling information at the mempool level. We could be optimistic in slightly different ways. There's like a whole bunch of things we can do better. The interaction with the WebSocket is kind of awkward, so there's like things to improve here, but it works pretty well for our purposes for now. The actually interesting thing that I wanted to talk about here is also like how the contracts interact. The idea of the board game is that sometimes you start a minigame, and then when the minigame ends, you need to get the results from the minigame back to know what's going on. And so you need to make sure that the contracts call each other, essentially. You want the board game contract to call the minigame and start it, and you want the minigame contract to call the board game contract with the results. And so you need to have composable atomic execution. And the way this works is that you send a transaction that contains blobs for both of the contracts at the same time. In order to settle that transaction, you need to have both blobs. This happens, for example, in the crash game backend logic, where when the transaction, when the game has ended, and this could be on the front end, but we did it on the back end because it's more convenient. We calculate what the end results should be, and then we create a transaction where there's both a blob for the chain action, so like for the mini game, and there's a blob for the game, like for the board game. Sorry, the names were super confusing, but so there's a blob for the crash game and a blob for the board game, and we send both of these at the same time in a single transaction. This is what actually gets sent on chain. Both blobs need to be correct for the game to be correct. And so what happens here is that each of these contracts has some logic to check that the information they receive is correct. And the way this works is in the ZK contract trait. So the ZK contract trait is the main trait for the smart contract logic that you write. And so in this execute function, we receive the call data, which is like the information about the transaction that we need verifying the execution. So we receive a game action blob, which is like the information for the board game. And if this information is, for example, the information for end minigame. So if the action says that we should be ending a minigame, then we're going to check that the contract that's calling us is the crash game contract. So is the contract that operates the minigame. At the same time, the contract that operates the minigame needs to make sure that the information sending to the board game is actually going to be correct and that somebody's not trying to cheat. So if you look at the execute function for the minigame contract, this is actually handled. What happens is that we make sure that the board game contract is receiving a game action blob with data that matches what we know to be correct. And so essentially we check explicitly that this function is in callee blobs what the comment says. When ending the minigame, we verify that the board game is being updated with the correct data. So we calculate locally what the correct data would be, and we check that the board game data that's being sent, like the blob being sent to the board game, matches what we expect. And so what that means is that you cannot prove the crash game blob unless you also have a correct board game blob. And the board game blob cannot be settled unless you also have a matching crash game blob. And so like both logic checks that what the other do is correct, essentially. You can't cheat. And the only way you're going to prove this end game transaction that I was showing is if both the crash game blob and the board game blob are correct. And so this is how you unlock composability, because even though you have proofs that are themselves independent, they can make assertions on what's happening on the other contracts, and you can make sure that the data is being correct and that it essentially works as if the crash game contract was literally calling the board game contract in a virtual machine with the information correct. It's kind of like something different you have to wrap your head around, but it works really well. And we've been using this for several of the actions. For starting a minigame, the same logic. If you want to distribute the rewards of the game, we need to do the same thing. We check that there's a transfer blob for the oxygen contract that exists. That's correct. When a player registers, we ensure that they've registered by depositing the amount of token they claim to have deposited. In the crash game, it's mostly just when you initialize or when you end. So this is how composability essentially works in those contracts. It's the same logic, kind of logic everywhere. There's a few other interesting things in the Orange Trail contract that I'm going to talk about quickly. So one of the things that we wanted to do, as I said, was doing this in real time. So the way this works is that so we have a notion of time in the Hyli blockchain logic. But that notion of time is going to be the time of the blocks, the block timestamp. And if you want to do things in real time, you can't use the block timestamps because you only have blocks around every second. So essentially, within the state of the application, we maintain our own version of time. that the backend updates via the Rollup system. Essentially, the Rollup maintains its own notion of time. And occasionally we check that the notion of time from the rollup matches kind of the notion of time on chain. And if it doesn't, then the transaction will be able to be settled. So we have like this synchronization mechanism that ensures that things aren't too weird. But because the rollup maintains its own notion of time, we can have real-time actions where the cash out happens at a given time, where the crash happens at a given time. And so these are all sent as transactions on chain, but like they're using different timestamp from the block timestamp, which is kind of a weird thing that you can do. Another interesting thing that we can do on Hyli for this rollup mode thing is that, well, as I was saying, because everything needs to happen on a rollup, it needs to happen in the same place, in the same lane. When I'm talking about lanes, I refer to lanes of the Autobahn consensus. We have blog posts on that if you're interested. But the question is, how do we ensure that transactions are indeed being sent to the correct lane? Well, this is actually something that you can do in a very easy way. Essentially, we store a lane ID in the state, and initially the lane ID is like a default value, which I think is just empty. So if the lane ID is a default value or it's beyond a certain timeout, what happens is that any transaction can change the current lane ID. So it essentially, this defines where the rollup is. It defines what the rollup operator is. And so you can once this is defined, any subsequent transaction needs to be on the same lane. And if it's not on the same lane, we fail the transaction, the proof is invalid, we cannot execute this, and so we ignore it. This allows us to do on-demand rollups, and it also really helps with censorship resistance because of the interaction timeline. So what you have here is essentially the code you need to write if you want to have a stage 2 rollup. You define a rollup, and then you can have timeout where, for example, say after 12 hours, any transaction can go through any of the lanes, and then you unlock the system if there was censorship resistance on the sequencer's part. And this actually uses a blockchain timestamp, not the rollup timestamp. So it's actually permissionless. And you see the same thing here on the board game. Cool. Another interesting quirk of the implementation of the crash game is that we actually have two slightly different versions of the same code living together. You have the on-chain version, which uses the minigame verifiable struct. This one contains stuff that becomes on-chain data. So essentially the state of the minigame, so who has cashed out, where we are in the game, who has cashed out so far. And then you have the backend information, which essentially, because this is like real time, so it's like 60 frames per second. This information isn't being sent on-chain as a transaction. This is just scattered by the backend data and used to send transactions for the cash out and things like that. But these are actually part of the same contract. The thing is that the on-chain contract cannot make any assertions on the data from the backend struct. It only makes assertions on the data from the verifiable struct. So if we have a crash transaction, we check the state is correct for the verifiable thing, but won't check anything about the backend because the backend trusts itself, essentially. The only real trust assumption you have is censorship resistance. You can't make invalid stuff happen. And the time is like the time of the rollup, so the rollup operator would have to do something super weird to be able to manipulate that. So you have like very limited manipulation opportunities, but you have some. So ideally, you'd be running this in a trust setup, but we've been running it on the back end because it was easier to do this way for the testnet. Anyways, the code for the backend applications itself is in the dgen party rollup execution folder. And like this basically reads the WebSocket, sends the transactions to the rollup, and then you have the tick. So for example, like the source behind the crash game, 60 times per second, we calculate the probability that we should be crashing. And if the probability is lower than some random value, then we send the crash transaction on chain and we actually stop the game. We manage, and like this is essentially all that happens on the crash game. The rest is kind of just boilerplate that could be done on a front end or skip potentially. And for the board game, it's the same thing. We just have some logic to make it easier to start mini games by writing the composable blobs. We have some permission logic for reward distribution so that things happen easily. But these are like just cron jobs essentially that we're running and that could be run in a permissionless manner. So that's kind of like the meat of the board game logic. The rest of it is just like a regular architecture. I think the Hyli video goes into more details about that. Hope this was helpful to better understand how to implement composability and Rollup-like systems on Hyli. If you have any questions, hop on our Telegram or Twitter or X account and get in touch.